Good morning, everyone. Today we are going to discuss about our project review 3, which is towards non-invasive diabetic detection, a fingerprint-based predictive analysis approach. Here are our team members. Now I am going to discuss about a problem statement. Traditional diabetes detection diagnosis relies on massive blood tests which limit frequent monitoring and reduce patient compliance. Emerging evidence suggests a strong correlation between fingerprint rich patterns and metabolic disorders, yet this potential remains unneutralized. Collecting enough fingerprint data with confirmed diabetics status can be difficult. The system may produce false prediction in some cases. The challenge is to develop a non-invasive fingerprint-based predictive model using ML to accurate detection diabetes tendencies, ensuring accessibility, comfort, and scalability in healthcare. Abstract. This project processes a non-invasive diabetic detection system using fingerprint analysis. A dataset of diabetic and non-diabetic fingerprint will be collected and preposed for future extraction. Diabetes is a common health problem and early detection is important for proper treatment. Most exciting methods require blood tests which are painful and inconvenient. This project presents a simple and non-invasive method to predict diabetes using fingerprint image. The fingerprints are processed and analyzed to ML and DL models such as CNN, Random Forest, and SVM will be trained and evaluated. The system outputs risk score prediction likelihood of diabetes. Objectives and hypotheses. Design a non-invasive diabetic pipeline that predicts diabetes status from fingerprint images. Build a future stack handcrafted demographic features like rich density, minus counts, pattern class, rich space variance, and proper proxies. And deep features like CNN embedding. Establish clinical performance with target metrics. Validate generalize across manners, scanners, and lighting and demographic via external validation. Access fairness and robust to model. Benchmark against non-invasive baselines. For example, by using body mass index, age, and family history, it will give the update. Deliver a deployable prototype suitable for screening settings.
Methodology. Data collection. Fingerprint images are collected from both diabetic and non-diabetic individuals along with their corresponding labels. Image processing. The collected fingerprint images are enhanced by removing noise, improving constant and resizing to a standard format. Feature extraction. Important fingertip features such as ridge, patterns, and textures information are extracted for analysis. CNN is used because it performs well in image-based feature extraction. Feature selection. Random forest is selected to handle complexity data. SVM is used for its effectiveness with high dimensional features and small datasets. Model training. Machine learning algorithms are trained using selected features to learn patterns related to diabetes. Model evaluation. The trained model is evaluated using metrics such as accuracy and reference code to measure performance. Prediction. The final model predicts the likelihood of diabetes and fingerprint inputs. Deployment. The trained model is deployed as a web application provided simple and non-invasive screening tool. System architecture. Understanding the core components. Web UI. Front end. User upload fingerprint images and input health parameters through a Flask-based web interface built in HTML using HTML, CSS, JS. Flag application server backend handles authentication, data routing, and prediction API endpoints. Image processing and feature extraction uses OpenCV to extract key fingerprint characteristics such as ridge count and pattern type. Machine learning learns learning inference engine. A random forest classifier processes the extracted biometric features combined with user health. Implementation of CNN. First, the system takes the fingerprint image as a input and cleans it. Then CNN layers detect the patterns like ridge and edges in the fingerprint. Polling reduces the system image size while keeping important details. Finally, it converts the image into future extractions. Implementation of RF. The system takes health details like BMI, age, and family history. It creates many decisions tree to analyze the data. Each tree gives a prediction. The final result is chosen by majority voting. Implementation of SVM. The system takes combined data. It processes and find the best boundary between classes. It separates data into low, medium, high risk groups. Finally, it gives the panel prediction. Existing versus proposal system.
Discuss about results of our project. The results of our project is key static on a performance matrix. We are using parameters like fingerprint, ridge count, age, BMI, family history. In what weightage they are considering here we have shown. And high accuracy database model database risk prediction. With logistics tree, this is the accuracy. With SVM and Asian tree, with random tree, 95% accuracy is there, and with normal process, it is nearly 90. So random forest is the best method to do this project. And confusion matrix. This is a confusion matrix given in our come in the output, and is the ROC graph. ROC means root of curve graph, and this is the curve graph. Means here we can see that fluctuating the graph of here when the values are increasing by day, means the data set increasing, and this is the confusion matrix. And thank you. That's all.